Good morning. In this video, I'm going to discuss about op-amp DC characteristics. First, let us see the introduction about the DC characteristic of an op-amp. One of the characteristic of an ideal operational amplifier is the output voltage will be zero for the zero input condition, and the current that is taken into the terminals of the operational amplifier will be equal to zero. But practically that is not happening. That is, a practical op-amp has some amount of DC voltage at the output for the zero input condition. That is, even if the input is zero, we'll be getting some amount of offset voltage at the output. And next, in practical op-amp, the current that is being taken from the source to the op-amp input, that is IB current, is also not equal to zero. And what causes this one? This is mainly due to mismatch in the transistor. That is, the op-amp input will be responding differently to the current and voltages that is being used for biasing the transistors in the operational amplifier. And one more thing is that a real op-amp response is also temperature dependent one. And next slides we are going to see about what are the non-ideal DC characteristics which will be adding some error or offset voltage to the DC output voltage. The first non-ideal characteristic is input bias current, and second one is input offset current, and next is input offset voltage, and the last one is thermal drift. Okay, these are the some of the non-ideal DC characteristics which is going to add some error output voltage to the DC output voltage. Now in this video we'll see about what is our input bias current. Input bias current. So here the figure shows the ideal operational amplifier, and as I already mentioned, the current for the ideal case, the current that has been entering into the terminals of the op-amp, that is IB minus and IB plus, is equal to 0. And here the figure shows a practical operational amplifier, but practically that is not the case. So the current that has been taken from the terminals of the op-amp is not equal to 0 for the case of a practical op-amp, and this causes mainly due to the transistor mismatch. Okay, next we'll see the condition what we call by IB1 and IB2. This IB1 and IB2 are called as a base current that has been entering into the inverting, that is a negative terminal, or non-inverting positive terminals of the op-amp. The average of these two base currents we normally called as a input bias current. So input bias current is nothing but the average of the current that will be flowing into the two input terminals of the op-amp for the practical case. So IB is written by IB plus IB minus divided by 2. So due to presence of this IB input bias current in the circuit, we'll be going to get some amount of error voltage or the output, even if both the input are going to be in a zero condition. Now let us see the inverting amplifier in presence of this input bias current in the circuit. Here the circuit diagram shows a normal inverting amplifier where Vi, that is the input, is being applied to the inverting terminal. Here negative is called as the inverting terminal, which is terminal number 2, and positive is a non-inverting terminal, that is terminal number 3. And if we see here, here the input we applied is 0, but due to presence of this IB current, that is this two base current, we are going to get some amount of error voltage at the output. Okay, so here I have mentioned that in the ideal cases we know that if my Vi is 0, my V0 has to be 0, but here the diagram shows that for the practical operational cases, if Vi is equal to 0, then V0 is not equal to 0. Why we are getting a DC output offset voltage? This is mainly due to presence of this input bias current in the circuit. So the output voltage in that case is given by IB into RF. RF is a feedback resistor. IB is a current that flows to the feedback resistor. So due to presence of this input bias current, we are going to get some amount of error voltage at the output, even if my input is in zero voltage condition. So now we'll see this with an example. So already the manufacturer have mentioned that for the bipolar operational amplifier, the amount of input bias current that will be entering into the terminals of the op-amp will take the value of 500 nanoamps. Now here we'll take a condition that if the feedback resistor I'm going to use in the circuit is 100 kilo ohms and my Vi is zero condition. So Vi is 0 and RF is 100 kilo ohms, and the transistor which you are going to use here in the internal part of the op amp is the bipolar. So your IB takes the value 500 nanoamps. So V naught will be equal to IB into RF. IB is 500 into RF is 100 kilo ohms. So we are getting a voltage of 0.05 volt. So even if my input is 0, I'm getting some amount of offset or error voltage at the output. Okay, so what is the technique we can use to make the output 0 for 0 input condition? So what is the compensation technique we can use to compensate for this input bias current? So this is an inverting amplifier with the bias current compensation. If you look at this diagram and the previous one, this diagram OR compensation resistor has been included in the circuit. This OR compensation resistor is used in order to compensate for the presence of IB current in the circuit diagram. Now let us see the analysis part of this one. So bias current compensation circuit. Okay, so now let if the voltage across is our compensation, we are considered as a V1 voltage, and the voltage difference between these two terminal voltages as per the ideal condition we are taking VD is equal to 0, and V2 is the current that is present, voltage present across the feedback resistor RF, and the I2 is the current that flows through the voltage V2, and I1 is the current that flowing through the resistor R1. Okay, now let us first apply KVL to this closed loop, that is starting from V1, V2 and 0, because this is going to form a closed circuit. So we can apply a KVL. So KVL, the voltage present here is given by minus. See the polarity, it is plus minus. So minus V1 plus VD plus V2 minus V naught equal to 0. Since your VD is 0, I have mentioned here as 0. So minus V1 plus VD is 0, that is differential voltage, plus V2 minus V naught equal to 0. From this V naught, if we take the V naught to the other end, V naught equal to V2 minus V1. So if I want to make my V naught equal to 0, I should keep my both the voltages V1 and V2 must be same. If this V1, the voltage across our compensation, and the voltage across feedback both are same, means I can make my V naught equal to 0 voltage for the 0 input condition. Let us consider that is equation number 1, and from the circuit diagram we are going to find what is V1. So V1 is nothing but, we are going to apply Ohm's law here. V1 is nothing but I into R formula. So the current that flows this OR compensation is given by IB plus. So V1 is equal to I into R, IB plus into OR compensation. We are going to consider that is from that IB plus is given by V1 divided by OR compensation. Let us consider that is equation number 2. And next, we are going to find what is the current I1 and I2. If you see the previous diagram, so if you see the previous picture, the voltage at the non-inverting terminals of -1, that is 0, is I1 is equal to V1 by R1. From the previous figure, it's clear that I1 is given by the formula V1 by R1, and I2, that is the voltage across this V2 is given by I2 into RF. So let us consider this is equation number 4, and we have seen the assumption that to make V0 is equal to 0, your V1 should be equal to V2. Okay, that is the first equation we got it. So if you are going to find, if you want to make V0 0, V1 and V2 equal to 0, so in the equation number 4, I'm going to substitute in the place of V2 as V1. So I2 will become V1 divided by R1, and that is considered to be equation number 5. Okay, now I'm going to apply at node A. Okay, I'm going to apply a KCL at node A. So the two current that are entering into that node A is given by IB minus. So IB minus is equal to I2 plus I1. So I1, what is I1 and what is I2? This two already we got from the equation number 3 and 4. So I2 is given by I2 is given by V1 by RF from the equation 5, and I1 is given by V1 by R1. So from this IB minus is equal to, if you take the V1 outside, 1 by RF plus 1 by R1, if you cross multiply, you'll get V1 into R1 plus RF by R1 into RF. Okay, consider that is equation number 6. And the main thing we have to assume here is that the current that is entering into the terminals of the op amp for this case is considered to be equal. That is, IB minus is equal to IB plus. So IB minus from the equation number 2 V1 by R compensation, IB plus from this equation number 6 it is given by V1 into R1 plus R2 divided by R1 plus RF. So from this equation your R compensation is given by this V1 will get cancelled. 1 by R compensation is equal to R1 plus RF by R1 into RF, where R compensation is equal to R1 parallel with RF. So this is the conclusion part. So what you infer from this is that by selecting proper value of all compensation, we can make V2 can be cancelled with V1 and V0 will become 0 for 0 input condition. So to compensate for the input bias current, the compensating resistor should be equal to the parallel combinations of R1 and R2. Okay, the reference book used here is Linear Integrated Circuit by Rai Chaudhary and Sylvie Jain. Okay, all in this video, I've discussed about one of the non-ideal DC characteristic which has been used add error to the output voltage, that is the input bias current, and what causes input bias current, and not to overcome the input bias current, what is the compensation thing to be added in the circuit, that is OR compensation resistor, and what is the value of the OR compensation has to be used to make the output voltage 0 for the 0 input condition. Thank you.